So I think this is pretty cool. This is I think it's a 1.5 micro Henry farad or millihenry farad I wound a while ago with a diode to stop the voltage spike when the power turns off. And this is here to kind of remedy the inrush current from these two batteries into the system and the wheel drivers down here, because it has cooked a few switches and it levels off to a low current, but when you turn it on, the current is really, really high. So I wasn't sure if this would work or not, but I just did this little capture function here. And here you can see we are measuring the voltage across the inductor when we turn the system on. And here's the positive and the negative leads. So when we turn the system on, you can actually see as stuff powers up on the board. There are these two bumps here. And the first one goes to 8 volts about, and the voltage across the inductor is the direct proportional to the current moving through it at any time. So this peak in voltage corresponds to a peak current change. And the good thing about the inductor is instead of having a flash of current, which can cook your switches or blow a fuse if you aren't lucky enough, the inductor kind of slows that down. You can't have an instantaneous current change through an inductor, so it generates a back voltage, back EMF. So here, I think the motor drivers must power on here, which are the big boxes down here. Those are dumb. And a split second later, I think the electronics turn on, or the fan right here, or it's all of these buck converters. It's probably the buck converters actually. So it's pretty interesting. And then the voltage levels off. So, and this is the voltage across the inductor. So now I got to go through and I'm curious to see what the peak current is here, because I know the voltage across the inductor and I know the inductance. I know the time it takes, but I'm not sure about the inductance. I calculated it a while back. So anyways, thought that was pretty cool.